Every science teacher you ever had told you the same thing. Space is silent. The vacuum has no air, no medium, so no sound. End of story. And they weren't wrong, but here's what they left out. Space is silent, sure. But space isn't empty. It's filled with plasma, magnetic fields, and literal ripples in the fabric of spacetime. And those things carry waves. Real ones. A supermassive black hole has been holding a single musical note for longer than complex life has existed on Earth. The sun is ringing like a bell right now. And in 2015, two merging black holes released more energy than every star in the observable universe combined. And that wave physically passed through your body. You didn't feel it, but it happened. Get comfortable. Hit subscribe if you're new here, because by the end of this, silence will never mean the same thing again. Now, let's slowly ease into this. Part 1. The silence that was never true. Picture this. You are standing on the surface of the moon, not in a simulation, not in a photograph actually there, boots in grey dust, looking out at a terrain that stretches in every direction without a single curve of horizon to comfort you. The sky above you is pure black, even with the sun blazing directly overhead, because there is no atmosphere to scatter that light into the blue ceiling we take for granted on Earth. And the silence is total, absolute. The kind of silence that has weight to it, that presses in on you from every side like the universe itself is holding its breath. You can watch rocks tumble down a crater wall and hear nothing. You can watch a fellow astronaut's boots crunch into regolith 3 meters away and hear nothing tear. You can watch what looks like a small explosion of dust where a micrometeorite just struck the surface at over 17 kilometers per second, and you hear absolutely nothing. The Apollo astronauts described this experience as one of the most disorienting sensations of the entire mission. Not the weightlessness, not the alien terrain, not even the fragile awareness that a few millimeters of suit material separated them from instant death. The silence. The complete, undeniable, total silence of a universe that did not seem to care whether they were there or not. And this experience, this profound, bone-level silence, became the foundation of one of the most widely accepted scientific facts most people carry around with them. Space is silent. Space has no sound. In space, no one can hear you scream a line so famous it became a movie tagline, a cultural shorthand, a thing you probably learned in school before you were old enough to fully understand why. And the reason you learned it is because it is, in a specific and important sense, completely true. Sound, in the classical definition, is a longitudinal pressure wave propagating through a medium. It is molecules bumping into molecules, compressions and rarefactions traveling outward from a source, and your eardrum detecting those compressions and converting them into the electrical signals your brain interprets as noise. No medium, no molecules, no bumping, no sound. The vacuum of space does not have enough molecules per cubic centimeter to support that kind of wave propagation, and so the biggest explosion you could possibly imagine, a star detonating, a planet colliding with another planet, a black hole tearing a companion star apart. All of that, by the textbook definition, makes no sound that a human ear could ever detect. That fact is not wrong. But here is the thing about facts that are technically correct. Sometimes they are also profoundly, dangerously incomplete in a way that leads you to a completely false picture of reality. And the false picture this particular fact creates is the idea that the universe is quiet, that it operates in silence, that all of this, the 100 billion galaxies, the trillions of stars, the black holes and neutron stars and millions of magnetars and colliding galaxy clusters, all of it plays out in a kind of celestial quiet that would feel peaceful if you could somehow witness it. That picture is wrong. Not slightly wrong, not wrong in a footnote, technical nuance kind of way, wrong in a way that inverts the entire experience once you understand it. The universe is not quiet. It has never been quiet. It has been producing real, physical, propagating waves through real physical media since before the first atom formed, and it is doing it right now in every direction, at scales and energies that make the sound of a nuclear weapon detonating feel like someone gently tapping a fingernail on a wooden desk. What we have to do first, before we get to the black holes and the gravitational waves and the note that has been playing for 2.5 billion years, is take apart the assumption underneath the assumption. Because the reason most people believe space is silent is not just that they heard it in school, it is that they have a specific, implicit mental model of what space actually is. And that model is wrong in a way that changes everything. Ask the average person what space is made of, and they will say nothing. Vacuum, emptiness, the void. Maybe they will mention that there are stars and planets and asteroids scattered around, but the stuff between those things, the interstellar medium, the space between galaxies, the regions that look completely black in any photograph, they imagine that as essentially nothing, as the absence of matter, as a place where the laws of physics apply, but where nothing is actually happening because there is nothing there for physics to happen to. And this is where the real story begins. Because space is not nothing. Space is not even close to nothing. The thing we call the vacuum of space, the thing that makes the word vacuum feel appropriate, is technically defined as having a very low particle density, somewhere around 5 particles per cubic centimeter in the interplanetary medium of our solar system. That sounds like nothing. 5 particles in a cube the size of a sugar cube. But compare that to the density of the interstellar medium in certain regions, or the intracluster gas that fills the space between galaxies in a galaxy cluster, or the plasma environment inside a stellar corona, and you start to realize that the universe contains an enormous range of densities, and many of those densities are absolutely sufficient to carry waves. Not metaphorical waves, real, physical, propagating disturbances. What we call sound, when we are being honest about the physics rather than the biology, the space between the sun and the earth is filled with the solar wind, a continuous stream of charged particles, electrons and protons and heavier ions, flowing outward from the sun at speeds between 300 and 800 kilometers per second. That is not nothing. That is a medium. A thin medium, yes. A medium with a particle density that would make the best vacuum chamber ever built in a human laboratory look like a thick soup by comparison. But a medium nonetheless. And embedded in that medium are magnetic field lines that stretch from the sun outward past the edge of the solar system, twisting and kinking and snapping and reconnecting, carrying electromagnetic oscillations that propagate through the plasma the way pressure waves propagate through air. These are real physical disturbances. They have frequencies. They have amplitudes. They carry energy from one place to another through a real physical medium. The only reason we do not call them sound is that our definition of sound was built by creatures who evolved in an atmosphere on a rocky planet and never needed to detect anything else. This is what I mean when I say the silence of space is a limitation of us, not of the universe. The universe does not care how humans define sound. The universe has been doing what it does for 13.8 billion years, long before anything existed that could define anything. Pressure waves, electromagnetic oscillations, magnetohydrodynamic disturbances, gravitational ripples in the fabric of spacetime. All of these are forms of wave propagation through physical media. All of them transfer energy. All of them, if you had the right kind of sensor tuned to the right frequency range and the right type of wave, would register as something, would sound like something. Would, in a very genuine physical sense, be sound. What you have instead of that perfect sensor is a pair of ears optimized for detecting pressure waves in a narrow frequency range in a nitrogen-oxygen atmosphere at roughly sea level on one specific rocky planet. You are, cosmically speaking, profoundly under-equipped for the task of listening to the universe, and the universe has been making noise about it ever since. So, what does fill space, if not nothing? Let us actually lay this out, because it matters for everything that comes after. Roughly 99% of all visible matter in the universe is in the form of plasma-ionized gas, atoms that have been stripped of their electrons by high temperatures or intense radiation, leaving behind a soup of free electrons and bare atomic nuclei. Plasma is not rare. Plasma is the default state of matter in the universe. The solid, liquid, and gaseous matter that makes up everything you have ever touched is the exception, not the rule. Stars are plasma. The gas between stars in a galaxy is largely plasma. The gas between galaxies in a galaxy cluster is plasma. The solar wind is plasma. The magnetospheres of planets are plasma environments. Plasma has physical properties, density, pressure, elasticity, magnetic permeability, and physical systems with those properties support wave propagation. This is not a stretch. This is not a metaphor. Plasma carries real acoustic waves, magnetoacoustic waves, Alfvén waves, and a variety of other disturbances that function physically the way sound functions in air. The medium is different. The frequency ranges are utterly alien compared to human hearing. The scales involved are incomprehensible in any intuitive sense, but the physics is the same. And, beyond plasma, there are magnetic fields. The entire solar system is threaded through with magnetic field lines. Galaxies have coherent magnetic fields spanning thousands of light years. Galaxy clusters have magnetic fields. These fields are not static. They oscillate. They carry energy. They interact with the plasma they are embedded in to produce waves that travel through that plasma. And then, at the most fundamental level, there is spacetime itself, the geometric fabric of the universe, that, as Einstein showed us, is not a passive backdrop, but an active physical medium that can be distorted, stretched, compressed, and set to vibrating by the motion of massive objects. Gravitational waves are ripples in spacetime. They are waves propagating through the most fundamental medium that exists. If that does not count as sound by some definition, then the definition needs to be larger. We are taught about the silence of space as a settled fact. But the more accurately you understand the actual physical environment of space, the more you realize that the silence is local. It is the silence of a thin patch of interplanetary vacuum that happens to surround the one rocky planet where listening creatures evolved. Zoom out from that patch, not even very far, cosmically speaking, and the picture transforms completely. What you find is a universe that has been vibrating, oscillating, ringing, humming, and propagating waves through every available medium since the beginning of time. A universe that does not require a listener. A universe that has been making noise in every direction without pause and will continue to do so long after every eardrum in existence has returned to dust. The question is not whether space makes sound. The question is whether we have the imagination to recognize what we are actually embedded in. And the answer to that question starts with the closest thing in the sky, the star that keeps you alive, the star that is ringing right now, at this exact moment, in a way that you were never built to hear. Part 2. Redefining sound without breaking physics. Before we go any further into what the universe is actually doing, we should take a moment to be rigorous about what we mean when we say sound, because this is the exact point where a lot of these discussions go sideways. Either someone overclaims space is full of sound, everything is sound, the universe is singing in a way that feels poetic but is scientifically sloppy, or someone overcorrects and insists that nothing outside of a pressure wave in air deserves the word sound at all, which is technically defensible but leads to a picture of the universe that is deeply misleading. The truth is somewhere more interesting than either of those positions, and getting to it requires being precise about the physics rather than the vocabulary. A sound wave, in its most fundamental physical description, is a longitudinal wave. This means it propagates by alternating compressions and rarefactions, regions where the medium is pushed together and regions where it is pulled apart, traveling outward from a source. In air, this means molecules being pushed closer together in the compression phase and spreading out in the rarefaction phase, with that pattern moving outward at roughly 343 meters per second at sea level on Earth, give or take, depending on temperature and humidity. The key physical requirements for this process are two things. First, the medium must have mass, and second, the medium must be compressible. It must be able to be pushed together and spring back. Air has both of these properties. Water has both of these properties, which is why whales can communicate across ocean basins. Steel has both of these properties, which is why you can hear a train coming by pressing your ear to the rail long before you can hear it through the air. The speed of sound is different in each of these media because their density and elasticity are different, but the fundamental wave mechanics are identical. Now, plasma. Plasma ionized gas, which, as we established, is the dominant form of visible matter in the universe, also has mass, and it is also compressible. This means plasma absolutely supports longitudinal pressure waves. This is not a theoretical possibility or an edge case. It is a straightforward consequence of the same physics that makes sound work in air. When you have a source that compresses a region of plasma, that compression propagates outward as a wave, just as it does in air. The frequency and wavelength of that wave will be governed by the density and pressure of the plasma, which in most astrophysical environments is vastly different from the parameters of Earth's atmosphere, which is why cosmic plasma waves typically operate at frequencies far outside human hearing, sometimes so far outside that a single wave cycle takes millions of years to complete. But the physics is continuous with the physics of sound in air. It is the same phenomenon, stretched across a different set of parameters. Beyond pure acoustic waves, plasma also supports a family of waves called magnetohydrodynamic waves, waves that arise from the interaction between the plasma and the magnetic field embedded within it. These include Alfvén waves, which are transverse oscillations of magnetic field lines that propagate along those field lines the way a wave propagates along a plucked guitar string, and magnetoacoustic waves, which combine the compressive properties of acoustic waves with the restoring force of the magnetic field. These are all real, physical, propagating disturbances in a real physical medium. They carry energy from one place to another. They can be detected, measured, characterized by frequency and amplitude and wavelength. Whether you want to call them sound is partly a semantic question, but physically they are cousins of sound in a way that is not metaphorical. They are wave propagation in a medium, full stop. And then there is a third category that is even more fundamental and even harder to argue with. Gravitational waves are ripples in the metric of spacetime itself. When massive objects accelerate, when two black holes spiral into each other, when a neutron star collapses, when anything with significant mass moves in an asymmetric way, they produce distortions in the geometry of spacetime that propagate outward at the speed of light. These distortions stretch and compress space itself as they pass. They are not pressure waves in a conventional medium, but they are wave propagation in the most fundamental medium that exists, the space-time fabric that underlies all of physical reality. They have frequencies, they have amplitudes, they carry energy away from their sources, and they interact physically with matter, including your body, when they pass through it. If you are going to argue that gravitational waves are not sound because spacetime is not a conventional medium, you are making an argument about semantics, not physics. The physics is unambiguous. These are propagating wave disturbances that transfer energy through a medium. What this gives us, then, is three distinct interpretations of what sound means, and three different ways to evaluate whether the universe is making it. The most restrictive interpretation, pressure waves in a gas or liquid with parameters similar to Earth's atmosphere, rules out most of what we are going to discuss. But it still allows acoustic waves in plasma, which means it still allows the Perseus black hole and the interior of the Sunday. The intermediate interpretation, any propagating wave disturbance in any physical medium, allows everything up to and including magneto-hydrodynamic waves. The broadest interpretation, any physical wave phenomenon that transfers energy through a medium, includes gravitational waves and brings the full picture into view. Pick whichever interpretation feels most honest to you. All three of them lead to the same conclusion: the universe is not silent. By the most conservative definition of sound that still has any physical content, the universe is producing real acoustic waves in real media right now, at scales and energies that are genuinely staggering. What makes this more than an academic definition debate is sonification, the practice of taking physical data that is not intrinsically acoustic, translating it according to some mapping, and rendering it as audio that humans can actually hear. NASA and various research institutions have been doing this for decades, and the results are not fake sounds invented to make the universe seem interesting. They are real, physical data expressed in a form that human ears can process. When NASA takes the pressure wave data from the Perseus cluster and shifts the frequency upward by 57 octaves, and we will spend a lot of time on the Perseus cluster. In a moment, the sound you hear is the actual, physical structure of the wave, just transposed into a range your ears can respond to. The timing relationships, the frequency characteristics, the amplitude envelope, all of that is real. You are not hearing a sound effect chosen to match a vibe. You are hearing real data expressed in a new medium. And the fact that we need that translation does not make the original any less real. It just makes us the limitation in the system. The deeper point here is one that keeps coming up throughout this entire topic, and it is worth stating explicitly before we go further. Human perception is not a window onto reality. It is a filter. It is a set of narrow, specific channels that evolution found useful for survival in a very particular environment over a relatively short period of geological time. We see a thin slice of the electromagnetic spectrum, the part the sun emits most strongly and the part that Earth's atmosphere is most transparent to, and call it visible light, as though other wavelengths are somehow less real. We hear a specific range of pressure wave frequencies that happen to be produced by the things that mattered to our ancestors: predators, other humans, wind, water, and we treat that range as though it is the definition of what sound is. Everything outside that range gets categorized as either infrasound or ultrasound, words that mean below hearing and above hearing, as though the human hearing range is the standard that other frequencies are measured against. It is not. The human hearing range is an accident of evolution. The universe does not know it exists. This is going to matter more and more as we go through what follows. The sun is ringing. Planets are broadcasting. Black holes are pressing waves through the plasma of galaxy clusters. Gravitational wave events are passing through your body on a regular basis. None of this was designed for your ears. None of it was produced by a universe that cared whether anything was listening. It is all just the physics, playing out at scales and in frequencies and through media that your biology was never equipped to register. And when we do translate these signals into something hearable, when we slow them down or speed them up or shift their frequencies or render their shapes as tones, what we get is not a simulation. What we get is a glimpse of the actual acoustic reality of the universe filtered through the one instrument we had available. And what that glimpse reveals is something that should genuinely change the way you think about the place you live. Part 3. The first crack. Space is not empty. We have established that the definition of sound is more flexible than the textbook version, and that plasma and spacetime are legitimate media for wave propagation. But there is still an intuition that needs to be addressed, and it is the intuition that even if we accept all of that in principle, surely space is still mostly empty, mostly vacuum, mostly the kind of environment where none of those wave-supporting media are dense enough or structured enough to actually carry anything. And this intuition needs to be dismantled carefully, because it is doing a lot of work in keeping the false picture of a silent universe intact. Let us start with actual numbers, because the range of densities in the universe is so enormous that talking about space as if it were a single thing is like talking about planetary surfaces as if everything from the Sahara to the bottom of the Mariana Trench were the same. Environment. In interplanetary space, the thin medium between the planets of our solar system, the particle density, is approximately 5 protons per cubic centimeter. That is genuinely sparse. That is a better vacuum than anything humans have ever manufactured in a laboratory. Our best vacuum chambers achieve pressures of around 10 to the negative 13 pascals, corresponding to particle densities of maybe a few thousand particles per cubic centimeter, orders of magnitude denser than the interplanetary medium. Space wins on emptiness in that comparison, and this is the environment that people are mostly picturing when they say space is silent. And for human-scale acoustic waves, they are right. The interplanetary medium cannot carry a pressure wave at any frequency that would register to human senses. But now move to a different environment. The solar corona, the outer atmosphere of the Sun, has a particle density of roughly 10 to the power of 8 particles per cubic centimeter. That is still thin by everyday standards, but it is 10 million times denser than interplanetary space. Move to the chromosphere, and the density climbs to around 10 to the 15th particles per cubic centimeter. Move into the solar interior, and you are looking at densities that climb to 150 times the density of water at the core. These are not vacuum environments. These are dense, hot, seething plasma environments where pressure waves not only propagate, but propagate with enormous energy. And the Sun is not a special case. Every star in the universe is a dense plasma ball generating acoustic waves continuously. Every stellar interior is a medium that supports sound. Move to galaxy clusters, the largest gravitationally bound structures in the universe. Between the galaxies in a cluster, there is a thin but real medium of hot plasma called the intracluster medium. In the Perseus cluster, which we are going to spend a lot of time on shortly, the intracluster medium has a density of around 10 to the minus 25 grams per cubic centimeter, extraordinarily thin by any terrestrial standard, but absolutely sufficient to support pressure wave propagation. And the reason it is sufficient is not just about density in isolation, it is about the scale. When the wavelength of a pressure wave is measured in tens of thousands of light years, the medium does not need to be dense in any human-relevant sense. It just needs to be physically real, and the intracluster medium absolutely is. Move to stellar remnants, supernova remnants, pulsar wind nebulae, the expanding shells of gas thrown off by exploding stars. These are plasma environments with densities ranging from extremely thin in the outer regions to quite dense in the compressed shell at the forward shock. In these environments, Pressure waves are a standard feature. The expanding shock itself is a wave. The turbulence behind the shock generates acoustic oscillations. The interaction between the remnant and the surrounding interstellar medium creates complex wave patterns that persist for thousands of years after the explosion. Supernovae are literally giant sound events in a medium that can carry them. They are just not events whose sound reaches us here on Earth, because the interplanetary medium between the remnant and us is too thin to carry the wave all the way. There is also the magnetic dimension of this picture, and it adds a layer that makes the acoustic argument even stronger. The universe is threaded everywhere by magnetic fields. Not just near stars and planets everywhere. The Milky Way has a coherent magnetic field that traces the structure of the galaxy's spiral arms, with a strength of a few microgauss over scales of tens of thousands of light years. Individual star-forming regions have much stronger fields that shape how gas collapses into new stars. Magnetar surfaces have fields of around 10 to the 15 Gauss, which is roughly a quadrillion times the strength of Earth's magnetic field. These fields are not passive. They are embedded in plasma, they interact dynamically with the plasma, and they carry wave energy in forms that are physically continuous with acoustic waves. When you include magnetohydrodynamic wave modes alongside pure acoustic modes, the fraction of the universe in which some form of wave propagation is occurring at any given moment becomes overwhelming. Here is a thought that should shift something in how you picture all of this. The statement that most physics teachers make that space is mostly empty is true in the sense that most of the volume of the universe contains very few atoms per cubic centimeter. But most of the mass of the universe, most of the energy, most of the physical activity, all of that is concentrated in the regions that are not empty: stars, stellar clusters, galaxies, galaxy clusters. And the medium immediately around these structures, the medium that connects them and fills the spaces between them, even that medium is not nothing. It is a thin plasma, threaded with fields, carrying waves, participating in the physical dynamics of the universe on scales that are genuinely difficult to conceptualize. Silence is not the default condition of the universe. Silence is what you get in the specific, local, thin patch of interplanetary vacuum where one species of biological organisms evolved. It is a regional phenomenon in a universe that is, on average, doing something acoustically remarkable at nearly every scale. And this brings us to a phrase that I think captures the situation better than almost any other. The sound of the universe is not absent. It is just outside our bandwidth. It operates at frequencies too low, in media too exotic, at scales too large, for the biological detection apparatus we were given. We are like people trying to appreciate a symphony while standing in a soundproof room looking through a window at the performers. We can see that something is happening. We can watch the musicians moving. We can see the strings vibrating. We can watch the conductor's arms sweeping through the air. But we cannot hear it. And the danger is that we conclude, from our soundproof room, that the symphony is not actually producing any sound. It is. We are just on the wrong side of the glass. And what we are about to discover, as we move from the general physics to the specific examples, is that the symphony has been playing for longer than the Earth has existed, at energies that are genuinely incomprehensible, and it is nowhere near finished. Part 4. The first hint of the symphony. Every principle we have built up so far, the real physical media of space, the legitimacy of plasma acoustics, the inadequacy of human perception as a measure of what the universe is doing, all of it converges on a single implication that we have been circling but not yet stated directly. The universe is not just capable of producing what we would call sound in a technical sense. It is doing it constantly, right now, in every direction, at every scale from the interior of the Sun to the spaces between galaxy clusters. The universe is propagating waves through real physical media. Not occasionally, not in rare dramatic events, continuously, as a baseline condition of its operation. To appreciate what this actually means, it helps to think about what a frequency spectrum for the universe would look like if you could map it all at once. Human hearing spans roughly 10 octaves, from 20 Hz at the low end to 20,000 Hz at the high end. An octave is a doubling of frequency, so this means we can detect sound waves whose frequency varies by a factor of about 1,000 from lowest to highest. That sounds like a lot until you compare it to the acoustic frequency range of the universe, which spans something closer to 30 to 40 orders of magnitude, depending on how broadly you define acoustic. At the high end, there are pressure waves inside neutron stars operating at kilohertz frequencies audible if you could somehow be in the right medium. At the low end, there are pressure waves in galaxy clusters that complete a single cycle in tens of millions of years. The ratio between these extremes is not 1,000, it is something like 10 to the 25th. Compared to that, our 10-octave hearing range is a single line on a canvas the size of a continent. And within that vast acoustic spectrum, there are specific phenomena operating at specific frequencies that represent some of the most energetic and structurally important processes in the universe. The sun's oscillations, sitting at a few millihertz, are a continuous resonance of the most important object in our cosmic neighborhood. The magnetosphere of Earth produces plasma waves that are technically in the audible frequency range, though not in a medium you could physically be exposed to. Pulsars, which we will return to in more detail, spin at rates from fractions of a hertz to hundreds of hertz, putting their periodic signals squarely in the audio band. The Perseus cluster's black hole, which is the most extreme example we are going to examine, operates at a frequency so low that the word frequency barely seems appropriate, roughly one cycle per 10 million years, which is 57 octaves below the lowest note a human can hear. Gravitational waves from merging stellar mass black holes sweep up through the audio band in the final seconds before collision, producing a characteristic chirp that LIGO detected as an audible tone. What all of these have in common, beyond their physical reality, is that they are not anomalies or edge cases. They are representative of categories of phenomena that occur throughout the universe all the time. There are approximately 100 billion stars in the Milky Way alone, and every one of them is a seething plasma ball with internal acoustic oscillations. There are several 100 billion galaxies in the observable universe, and every galaxy cluster contains a hot intracluster medium that can carry pressure waves. There are millions of pulsars throughout the universe, each one a cosmic metronome, broadcasting structured periodic signals in all directions. Gravitational wave detectors are now detecting black hole and neutron star merger events multiple times per week. These are not rare spectacles. They are the normal operating condition of the universe at large. The Perseus black hole is going to be our anchor for the extremes of what all this means. We will get there. And when we do, the numbers involved are going to do something genuinely strange to your intuitions about what sound is capable of. But before we go to the extremes, we need to start closer to home, with the loudest acoustic source in our own solar system, a source that is 93 million miles away from you, a source that has been ringing continuously for 4.5 billion years, a source whose acoustic energy output is so enormous that comparing it to anything on Earth requires a kind of numerical vertigo. You experience the electromagnetic output of this source every day. You have probably never thought about it as something that also has a sound, but it does. It has been making that sound longer than the Earth has existed. And the sound it makes, when translated into a form human ears can process, is one of the most alien things you have ever heard. Part 5. The Sun is Ringing. In 1960, a solar physicist named Robert Layton was analyzing Doppler shift measurements of the Sun's surface when he noticed something unexpected. The surface of the Sun was moving, not just convecting and boiling in the way that solar physicists already understood it was oscillating, rhythmically, with a characteristic period of about 5 minutes. The surface of the Sun was rising and falling, with a period of roughly 300 seconds, and the oscillation was coherent over large spatial scales. This was not the turbulent churning of hot plasma in a convection zone. This was something that had the characteristic signature of a resonant mode. Something inside the Sun was ringing. What Leighton had discovered, though, it took another decade and a half for the full theoretical picture to emerge, was helioseismology, the study of the Sun's interior through the analysis of its acoustic oscillations. It turns out that the Sun is not just occasionally vibrating. The Sun is vibrating in millions of simultaneous resonant modes, all overlapping, all interfering with each other, all driven by the continuous churning of its convection zone, all constrained and shaped by the physical structure of the solar interior. The 5-minute oscillation that Leighton noticed was one of the dominant surface expressions of these modes, but it was just the most obvious peak in what is actually a rich, complex, continuous spectrum of oscillations spanning a wide range of frequencies. The specific type of oscillation that dominates what we observe are called P modes, pressure modes, and they work exactly like sound waves in a resonant cavity. Imagine a glass sphere filled with a dense, hot plasma. Now imagine that the pressure fluctuations inside this sphere, driven by convective turbulence near the surface, create acoustic waves that propagate inward. As they travel inward, the density of the plasma increases, and the wave is refracted, bending it back upward toward the surface. When it reaches the surface, it reflects back inward. The result is a wave that bounces back and forth inside the Sun, gaining energy from the convective motions and losing it through radiation, settling into a set of resonant modes determined by the physical structure of the interior. These are standing waves inside the Sunday. These are the Sun ringing. This is not a metaphor. This is literally what is happening right now in the object that is currently shining through whatever window you are near. The frequencies of these oscillations cluster around 2 to 4 millihertz, 2 to 4 thousandths of a hertz. Compare this to the lowest note on a standard piano, which is A0 at 27.5 hertz. The Sun's dominant acoustic modes are roughly 10,000 times lower in frequency than the lowest note on a piano. Compared to the lower limit of human hearing at 20 hertz, the Sun is about 10,000 times too low. You could never hear it directly, not because it is not there, and not because it is too quiet, but because your eardrums oscillate at frequencies thousands of times higher than the Sun's ringing. The mismatch is not a matter of degree, it is structural. You were built for a different frequency range than the one the Sun operates in. But here is what makes this more than academically interesting. The energy involved in these solar oscillations is staggering. The acoustic energy density of the Sun's oscillations, the energy packed into these waves, is estimated at around 10 to the 26th joules. For context, the entire current world energy consumption of humanity is roughly 6 times 10 to the 20th joules per year. The acoustic energy locked into the Sun's ringing modes represents something like 10 million years of total human energy consumption. It is not a subtle wiggle. It is a genuinely energetic oscillation that involves the entire solar interior, a body with a mass 2 times 10 to the 30th kilograms, resonating in a set of modes that scientists can measure from Earth using the Doppler shift of light from the surface. And the reason helioseismology matters beyond the pure acoustic spectacle is that these oscillations are how we see inside the Sunday. We cannot send probes into the solar interior. We cannot directly measure the temperature, density, or composition of the Sun's core. But because different acoustic modes probe different depths, some stay near the surface, others plunge deep into the interior. The frequencies of these modes encode information about what the interior is made of, how it is structured, how quickly it is rotating at different radii. By analyzing the frequencies of the Sun's oscillations, helioseismologists have been able to map the interior of the Sun with a precision that would otherwise be completely impossible. It is the same principle that geologists use to study Earth's interior through seismic waves from earthquakes, the planet's own acoustic environment, revealing its inner structure. The universe, in other words, uses sound as a diagnostic tool, and we have learnt to listen. NASA and the European Space Agency have made recordings properly, sonifications of these solar oscillations. The raw signal is shifted upward in frequency by a factor that brings it into the human hearing range. And what you hear when you listen to these recordings is something genuinely remarkable. Not the chaotic roar of an explosion, not the random noise you might expect from a churning ball of plasma. What you hear is something almost musical, a deep, complex, organ-like tone with overtones and harmonics that shift and evolve over time, reflecting the millions of simultaneous oscillation modes interfering with each other. It sounds like a massive, slow chord being held by an instrument the size of the solar system. And when you hear it, knowing what it represents, the experience is genuinely affecting in a way that a description of it cannot fully convey. The closest star, the source of all energy on Earth, has been holding this note for 4.5 billion years and will continue to hold it for another 5 billion. The orchestra does not stop, it just expands. Part 6. The Solar System Orchestra. If the Sun is ringing, and the universe is continuously generating waves through real physical media, then the question is not whether our solar system is acoustically active. The question is how acoustically active, and what each component sounds like when translated into a form we can actually perceive. The answer, it turns out, is that nearly every major body and region in our solar system is constantly broadcasting something, and that the totality of these signals constitutes an acoustic environment that would be overwhelming if you somehow had the sensory apparatus to register it all simultaneously. Start with Earth itself, or rather with the region immediately surrounding it. Earth's magnetosphere, the region of space where our planet's magnetic field dominates the local environment, is a plasma environment, and like all plasma environments, it supports electromagnetic oscillations. One particular type of oscillation is called chorus waves, and these are among the more remarkable things that happen right above your head every single day. Chorus waves are produced when electrons spiraling along Earth's magnetic field lines interact with Whistler mode waves, a type of electromagnetic wave that propagates along magnetic field lines in a plasma. The result is a structured, rising tone emission that, when detected by a spacecraft and shifted into the audio range, sounds uncannily like a dawn chorus of birds. Not approximately like birds, startlingly, unnervingly like birds. Rising, chirping, overlapping tones that could convince you, if you heard them without context, that you were listening to a forest at sunrise rather than plasma waves in the near-Earth environment. This is not a coincidence of analogy. It is a direct translation of physical wave structure into audio, and the structure happens to produce something that your pattern recognition systems, tuned by millions of years of evolution to recognize biological signals, immediately interprets as life. There is also the phenomenon called Schumann resonances, electromagnetic resonances of the cavity formed between Earth's surface and the lower ionosphere. Lightning strikes around the globe, striking the Earth roughly 100 times per second, constantly excite this cavity. The fundamental frequency of this resonance is about 7.83 Hz, just below the lower limit of human hearing. It produces harmonics at 14, 20, 26 Hz and above. This is a standing electromagnetic wave that circles the entire Earth, continuously driven by global lightning activity. It is not a sound wave in the strict sense, but it is a real physical oscillation of the planet's electromagnetic environment, driven by continuous energy input from atmospheric electrical activity, and it is happening right now at the frequency range where your ears begin to respond. If you could somehow hear it, and some people believe very low-frequency electromagnetic fields may be detectable by certain biological systems, though this remains controversial, it would sound like a barely audible hum at the edge of perception. Move outward to Jupiter, and the picture becomes more dramatic. Jupiter's magnetosphere is the largest coherent structure in the solar system, dwarfing even the Sun in terms of physical extent. It stretches about 750 million kilometers in the direction away from the Sun and generates auroral radio emissions that are the strongest in the solar system other than the Sun itself. The Juno spacecraft, in orbit around Jupiter since 2016, has recorded these emissions and translated them into audio. What comes back sounds like a crackling, sizzling, dynamic soundscape, bursts of noise layered over each other, rising and falling in intensity, punctuated by sharp Whistler events when lightning in Jupiter's atmosphere couples energy into the magnetosphere. This is not the majestic silence of the solar system's giant. This is an electromagnetic cacophony produced by the most intense planetary magnetic field in the solar neighborhood. Saturn adds its own voice. Saturn's radio emissions, called Saturn kilometric radiation, are tied to its auroral activity and rotate with the planet, giving them a pulsed quality that reflects Saturn's rotation period. When sonified, they sound like rhythmic, oscillating tones overlaid on a background hiss, with a kind of alien regularity that reflects the periodicity of Saturn's rotation. Saturn's rings also produce their own electromagnetic signals, ring electrostatic discharges from lightning in the ring system, adding another layer to the planet's acoustic identity. Each planet has a distinct electromagnetic signature, a unique combination of magnetic field geometry, rotation rate, plasma environment, and energy sources that produces a soundscape unlike any other. The solar system is not a silent place. It is a place where the wrong kind of ears are listening. All of this brings us back constantly to the central point. The universe is producing real physical waves through real physical media at every scale and in every environment. We have established it in principle, we have confirmed it in our own solar system, and now the question is, what happens when we look beyond? When we find environments where the media are denser, the energy sources are more extreme, and the waves that result have properties that push every human intuition about sound to its absolute breaking point. Part 7. Pulsars. Cosmic metronomes. In 1967, a 24-year-old PhD student named Jocelyn Bell was working through a paper chart of radio telescope data, actual paper, printed by a chart recorder, when she noticed a repeating signal that appeared once every 1.33 seconds, with an uncanny precision that seemed almost impossible for a natural source. She brought it to her supervisor, Anthony Hewish, and for a brief, genuinely strange period, the signal was catalogued internally as LGM1, where LGM stood for Little Green Men. Not because anyone seriously believed it was alien, but because they could not immediately think of any natural physical process that could produce a signal that regular, that consistent, that precisely timed. The universe, it seemed, was not supposed to be this metronomic. What Bell had discovered was the first pulsar, a rapidly rotating neutron star emitting a beam of radio waves from its magnetic poles. A neutron star is what remains after a massive star collapses in a supernova. It packs roughly 1 to 2 solar masses into a sphere about 20 kilometers across, which gives it a density comparable to an atomic nucleus extended over an object the size of a city. The collapse that creates a neutron star conserves angular momentum, and since the progenitor star's core was much larger before collapse, the neutron star spins at an enormous rate. The fastest known pulsar, PSR J 1748-2446 AD, rotates 716 times per second, 716 revolutions per second. It has been doing this for millions of years. It is an object denser than a white dwarf, spinning at a rate that puts its equator at roughly 1/4 of the speed of light, and as its magnetic field offset from the rotation axis sweeps that radio beam around like a lighthouse, it produces a pulse every time the beam sweeps across your line of sight. If you point a radio telescope at this object and translate the pulses into audio, you hear a buzzing, almost mechanical tone at 716 Hz, squarely in the middle of the audible range. You are hearing, in a direct physical sense, the rotation of a dead star the size of a city. The Crab pulsar, the remnant of a supernova that astronomers observed in 1054 AD, recorded by Chinese and Arab astronomers as a star bright enough to be visible in daylight, rotates about 30 times per second, 30 Hz. That is below the lower limit of musical pitch perception, but well within the range that produces a sense of rhythm or buzz. Sonified recordings of the Crab pulsar sound like a steady, low thudding, the heartbeat of an object that was born in an explosion visible to the naked eye nearly 1,000 years ago and has been ticking with atomic clock precision ever since. The connection to our central story is direct. This is real physical wave propagation. Electromagnetic waves, structured by the rotation of a physical object, translated faithfully into audio. The pulsar is literally producing a signal that, when translated, falls in the audio range, not because we chose parameters to make it so, but because the physics placed it there. The deeper reason pulsars matter in the context of cosmic acoustics is what they tell us about structure and rhythm at the largest scales. Pulsar timing arrays, networks of radio telescopes monitoring dozens of pulsars simultaneously, have recently been used to detect the gravitational wave background, the low-frequency hum of gravitational waves from supermassive black hole mergers across the universe. The pulsars act as the arms of a galaxy-scale gravitational wave detector, their timing precision so extreme that tiny perturbations in the arrival times of their pulses, perturbations caused by gravitational waves stretching and compressing the space between us and the pulsar, can be detected and characterized. The cosmic metronomes are, in other words, our ears for the deepest sounds in the universe. And what they are beginning to hear is remarkable. Part 8. Transition, where sound breaks down. We have moved from the Sun to the outer planets to pulsars, and at each step the sounds have gotten stranger, the frequencies more extreme, the media more exotic. The acoustic landscape of the universe, even before we get to the most extreme examples, is already operating so far outside the parameters of human perception that describing it requires constant translation and constant reminding that these are real physical phenomena, not metaphors. But now we reach a conceptual boundary that is worth pausing at and examining carefully, because what is on the other side of it will require letting go of some intuitions that have been load-bearing so far. So far, all of the waves we have discussed, solar oscillations, magnetosphere, chorus waves, planetary radio emissions, pulsar signals, have been waves in conventional media. Plasma, electromagnetic fields, the hot gas inside a star. These are physical substances in the ordinary sense. They have mass, they have density, they can be compressed and stretched, and the waves they carry are cousins of the sound waves in air that we have been using as a reference point throughout. But what comes next inhabits a stranger regime, a regime where the wave propagates not through a substance but through the geometry of spacetime itself, where the frequencies are so low that a single cycle takes longer than recorded human history, and where the energies involved are so large that all of human civilization's total energy output is irrelevant for comparison. This is where sound, in the broadest and most physically honest sense, becomes almost unrecognizable. Consider what we mean by frequency in this context. Frequency is cycles per second, the number of times a wave completes a full oscillation in 1 second. A concert A is 440 cycles per second. The lowest note a human can hear is about 20 cycles per second. The lowest note a human can feel as a physical vibration, rather than hear as a pitch, is around 1 cycle per second. Below that, waves are classified as infrasound, and while humans cannot hear them, they can still have physical effects. Large infrasound sources can cause disorientation, nausea, even structural damage to buildings. Keep going lower, to frequencies of 1 cycle per hour, 1 cycle per day, 1 cycle per year, and you are now talking about oscillations that complete 1 full cycle over timescales we use to organize our lives. 1 cycle per million years. 1 cycle per 10 million years. These are not frequencies in any intuitive sense. They are geological rhythms, cosmological cycles, phenomena that have a frequency in the same mathematical sense that a heartbeat has a frequency, but that unfold over timescales that dwarf any human reference point. This is where the Perseus cluster black hole lives, and this is where everything we have established about cosmic acoustics reaches its most extreme expression. Before we get there, though, we should establish what makes the transition between conventional acoustic waves and these extreme low-frequency phenomena so conceptually jarring. It is not just the frequency, it is the wavelength. For a given wave speed, lower frequency means longer wavelength, the spatial distance between one peak of a wave and the next. A musical note at 440 Hz in air has a wavelength of about 78 centimeters. The same note at 440 Hz in steel would have a wavelength of about 12 meters, because sound travels faster in steel. Acoustic waves in the sun have wavelengths ranging from tens of thousands of kilometers to the full radius of the sun itself. And the pressure waves in the Perseus cluster, driven by the jets of a supermassive black hole, propagating through the hot intracluster plasma, have wavelengths of tens of thousands of light years. A single wave, from crest to trough, spans a distance that would take light 30,000 years to cross. This is not a wave in any sense that our intuitions were built to handle, but it is a wave. A real, physical, measurable pressure wave in a real, physical medium, and it has been propagating for 2.5 billion years. Part 9. The Perseus Black Hole. A note held for 2.5 billion years. In 2003, astronomers using NASA's Chandra X-ray Observatory were analyzing the X-ray emissions from the Perseus cluster, a galaxy cluster about 240 million light-years from Earth, containing thousands of galaxies embedded in a vast halo of hot plasma at temperatures of tens of millions of degrees. The intracluster gas in Perseus emits X-rays because it is so hot, and Chandra can image this emission with extraordinary precision, revealing the detailed structure of the plasma on scales of thousands of light years. What the astronomers found in their data was something they had not expected. The X-ray images of Perseus showed a pattern of concentric ripples in the plasma. Waves. Real, physical, propagating waves moving outward through the intracluster medium from the center of the cluster, where a supermassive black hole sits at the heart of the galaxy, NGC 1325A. These ripples were not metaphorical. They were not an artifact of the data processing. They were real variations in the density and temperature of the plasma compressions and rarefactions, alternating, propagating outward at the local sound speed in the plasma. In other words, they were sound waves, real acoustic waves, propagating through a real plasma medium, driven by the jets of energy blasting out of the central supermassive black hole. The black hole, which has a mass somewhere around 300 million times the mass of the Sun, was accreting material and launching jets of plasma and energy outward along its rotation axis. Those jets plowed into the surrounding intracluster medium, pushing plasma aside and driving waves outward, the same basic mechanism that causes a jet aircraft to produce a sonic boom, just scaled up by a factor of roughly 10 to the 25th. The frequency of these waves, the rate at which wave crests pass any given point, is approximately 1 cycle per 10 million years. Let that land. 10 million years for one complete oscillation. One crest, one trough, and back to a crest, over a span of time that is roughly twice the entire history of the genus Homo on Earth. If you were to express this in standard musical terms, it falls 57 octaves below middle C. For reference, middle C is 261 Hz. 57 octaves below that means dividing 261 by 257 times, which gives a frequency of approximately 10 to the minus 14 Hz, roughly 0.000000000000001 Hz. This is the note the Perseus black hole is playing. A B-flat, by the way, according to the astronomers who calculated it, the note whose frequency, when shifted upward through 57 octaves, lands closest to B-flat in the standard Western scale. The wavelength of this wave is tens of thousands of light-years. The wave has been propagating through the Perseus cluster plasma for approximately 2.5 billion years. 2.5 billion years ago, on Earth, complex life had not yet appeared. The most complex organisms on the planet were single-celled eukaryotes, cells with nuclei, more complex than bacteria, but nothing that you would recognize as multicellular life. Photosynthesis had been running for 1 billion years already, and the atmosphere was gradually accumulating oxygen. But in 2.5 billion years, nothing like a nervous system, nothing like an ear, nothing even remotely like the kind of organism that could recognize this note had yet come into existence. And this wave was already propagating. It had already been pushing through the plasma of Perseus for hundreds of millions of years before Earth even existed as a planet. NASA has released a sonification of the Perseus black hole's pressure waves. To produce it, they took the actual X-ray data, the physical measurements of the plasma density variations, and shifted the frequency upward by 57 octaves, bringing it from the unimaginably low frequency at which it actually operates into a range that human ears can process. What you hear is a low, ominous, slowly evolving tone with a quality that is genuinely difficult to describe. Not loud in the way that an explosion is loud, more like a subsonic presence, something felt as much as heard, with harmonics that shift and evolve as the wave structure of the cluster changes. And knowing what it represents, knowing that this is actual data from a real wave that started when complex life did not yet exist on Earth and is still propagating today, the experience of hearing it has a quality that is hard to categorize as anything other than genuinely affecting. This is not a sound effect. This is a physical fact expressed in a form that human biology can register for the first time after 2.5 billion years of playing to an empty room. The Perseus cluster is not unique. X-ray observations of other galaxy clusters have found similar structures, ripples, and waves driven by the activity of central supermassive black holes propagating through the intracluster medium. The Virgo cluster, the Centaurus cluster, Abell 2029, all of them show evidence of pressure waves in their hot plasma. This is a common feature of galaxy clusters, not an anomaly. Supermassive black holes, accreting material and launching jets, continuously drive waves into the surrounding plasma. They are the bass section of the cosmic orchestra, not the loudest in terms of peak energy, not the highest in frequency, but the most sustained, the most fundamental, the notes that have been playing the longest and that give the whole structure its lowest tonal foundation. There is something in the Perseus result that goes beyond the physics, though the physics alone is more than enough to justify the wonder. It is the idea of a note that has been playing without pause for longer than Earth has existed, and that is playing right now, and that will continue to play long after everything currently alive on Earth is gone. The universe does not require a listener. It does not need anything to be there to register its activity. The black hole at the center of Perseus does not know or care that there are observers 240 million light-years away who have built telescopes sensitive enough to detect its acoustic output and translate it into something audible. It just does what it does, driven by the physics of accretion and jet formation and plasma dynamics. And the waves go out, and they travel, and they have been traveling since before multicellular life existed on Earth. That is the scale of what we are talking about. And the Perseus note, as deep and ancient and remarkable as it is not the end of this story. It is not even the loudest thing we have detected. Part 10. What deep really means. The Perseus black hole gives us the deepest measured note in the universe, 57 octaves below middle C, a frequency so low that the word frequency feels almost inappropriate. But to fully appreciate what this means, and to build the bridge to the even more extreme events that follow, it is worth spending time on what the word deep actually signifies in acoustic terms, and on the gap between the range of the universe's acoustic activity and the narrow slice of it that human perception can access. The human ear is sensitive to frequencies between roughly 20 and 20,000 Hz. This is an evolutionary adaptation shaped by the acoustic environment of our ancestors, the frequency ranges of human speech, the calls of other animals, the sounds of wind and water, and the physical environment that mattered for survival. Frequencies below 20 Hz are called infrasound. We cannot hear them, but we can sometimes feel them as vibrations, especially at high amplitude. Frequencies above 20,000 Hz are called ultrasound. Dogs can hear up to about 65,000 Hz. Bats use frequencies up to 110,000 Hz for echolocation. Dolphins communicate at up to 150,000 Hz. But even the most sensitive biological hearing apparatus on Earth tops out somewhere below 200,000 Hz. Compare this to the electromagnetic spectrum. The frequencies of visible light are around 400 to 700 terahertz, 10 to the 14th hertz. And this is just the narrow band that corresponds to the Sun's peak emission and Earth's atmospheric transparency. The full electromagnetic spectrum runs from frequencies near zero to gamma rays at 25 times 10 to the 23rd hertz. Biology, as a sensing apparatus, has access to a profoundly narrow slice of physical reality. For acoustic phenomena in the universe, the situation is even more extreme. The frequencies at which cosmic acoustic events operate span an almost incomprehensible range. Pressure waves inside neutron stars operate at frequencies from tens of hertz to kilohertz, actually in the audible range, but in a medium no biological organism can access. The Sun's P-mode oscillations sit at a few millihertz, about 10,000 times below the lower limit of human hearing. Acoustic waves in stellar coronae and stellar winds operate at similar frequencies. The plasma waves in Earth's magnetosphere include chorus waves that, when sonified at their actual frequency, are already in the audible range around 1 to 10 kilohertz, because the plasma parameters happen to put them there. And at the extreme low end, the Perseus cluster and similar objects operate at frequencies of 10 to the minus 14 Hz, requiring compression of time by a factor of hundreds of billions to bring them into an audible range. The thought experiment that makes this visceral is this. Imagine that your hearing spanned the full acoustic frequency range of the universe, rather than the narrow 10-octave window it actually covers. Imagine that you could hear a wave, completing one cycle per 10 million years, just as clearly as you can hear a wave completing 400 times per second. What would the universe sound like? It would be overwhelming. There would be the constant, organ-like resonance of billions of stars all ringing simultaneously, each in its own set of modes, each a slightly different note determined by its mass and age and composition. There would be the rhythmic clicking of millions of pulsars, each at its own precise frequency, some of them in musical harmony with others, and most of them not. There would be the deep, almost sub-perceptual bass of galaxy clusters, waves too low, even in this expanded range to register as pitch, but felt as a kind of constant, ancient pressure. There would be the sharp transients of gravitational wave events, brief chirps that sweep upward in frequency and then cut off, each one the signature of two massive objects merging somewhere in the observable universe. What you actually experience, standing in the physical universe with your actual biology, is none of this. You experience near silence, the sounds of your own environment, the acoustic output of the thin atmosphere of one specific rocky planet, the biological noise of your own body. This is not a metaphor for human limitation in some philosophical sense. It is a literal, physical description of the gap between what the universe is producing and what your biology can detect. We exist inside a continuous acoustic event of staggering scale and complexity, and we perceive essentially none of it. The sonifications that translate cosmic signals into audible tones are, in a real sense, the closest thing we have to a hearing aid for the universe, a tool that allows our evolved sensory apparatus to make contact, however, approximately, with an acoustic reality that has been here all along. Part 11. The loudest event ever detected. On September 14th, 2015, at 5:51 in the morning Eastern Daylight Time, two detectors belonging to the Laser Interferometer Gravitational Wave Observatory, LIGO, registered a signal. The Hanford detector in Washington State registered it first. The Livingston detector in Louisiana registered it 7 milliseconds later, 7 milliseconds being the light travel time between the two sites, consistent with a signal traveling at the speed of light from a specific direction on the sky. Computers flagged the event in real time. The signal had a specific, characteristic shape, a rising frequency chirp that climbed from about 35 Hz at the start of detection to a peak of around 150 Hz just before the signal reached its maximum amplitude, and then cut off sharply. This is the waveform that general relativity predicts for the inspiral and merger of two compact objects, two black holes circling each other at increasing speed and decreasing separation, losing energy to gravitational waves, spiraling inward until they collide and merge in a fraction of a second. The two black holes were 36 and 29 solar masses respectively. They had been orbiting each other for billions of years before the final inspiral, spiraling inward as gravitational wave emission carried away energy and angular momentum, gradually tightening their orbit over immense timescales. In the final second before merger, the second that produced the signal LIGO detected, they were moving at a significant fraction of the speed of light. The merged remnant black hole was 62 solar masses. The total mass of the two progenitors was 65 solar masses. The missing 3 solar masses, the difference between 65 and 62, were converted into gravitational wave energy and radiated away in that fraction of a second. 3 times the mass of the Sun, converted entirely into energy and radiated as gravitational waves in the time it takes you to blink. To put this in perspective, the Sun converts about 4 million tons of mass into energy every second through nuclear fusion. This has been going on for 4.5 billion years. In that entire time, the total energy output of the Sun is an enormous number, but it is a number that can be calculated. The GW 150914 event, the designation given to this first detected gravitational wave event, released approximately 3 times the mass energy of the Sun in a fraction of a second. Not 3 times the Sun's annual energy output, 3 times the entire mass of the Sun, converted to energy according to E equals mc squared. This event was, at its peak, emitting gravitational wave energy at a rate of approximately 3.6 times 10 to the 49 watts. The total electromagnetic power output of every star in the observable universe combined is estimated at about 4 times 10 to the 49 watts. These two numbers are comparable. At its peak, this single gravitational wave event was briefly emitting as much power in gravitational waves as the entire observable universe emits in light. This is, by any reasonable measure, the most energetic acoustic event ever detected by human instruments. What LIGO actually measured was not a pressure wave in a gas, it was a strain in spacetime, a stretching and compressing of the geometry of space itself as the gravitational wave passed through the detector. The strain amplitude was about 10 to the minus 21, meaning that for every meter of distance in the detector's arms, the arms were stretching and compressing by about 10 to the minus 21st meters. This is 1,000 times smaller than a proton. This is so small that the concept of measurement breaks down under ordinary circumstances. LIGO can only detect it because it uses laser interferometry to compare the lengths of 2 4-kilometer arms simultaneously, and because it is sensitive enough that quantum effects from individual photons become a relevant source of noise. The fact that we built an instrument capable of detecting a strain this small is one of the more impressive achievements in the history of experimental physics. And the signal it detected, when the waveform was sonified and played back at actual frequency, is a brief, rising tone, a chirp that climbs from a low rumble up through a clear note and then cuts off. Less than a second of audio. The sound of 2 black holes merging. Since GW 150914, LIGO and its European partner Virgo have detected more than 90 gravitational wave events. Black hole mergers, neutron star mergers, and mixed events. Each one is a gravitational wave burst passing through Earth, compressing and stretching every physical object on the planet, including every human body as it goes. Each one is, in raw energy terms, an event that dwarfs anything else in the observable universe. And none of us feel them, none of us know, in any biological sense, when a gravitational wave is passing through our bodies. We are completely transparent to them, and they to us, except for that one extraordinary instrument in Washington State and Louisiana that was specifically built to notice what our bodies cannot. Part 12. The Wave Passed Through You. September 14th, 2015, at 5:51 in the morning, Eastern Daylight Time. While LIGO was registering that gravitational wave chirp, most people in the eastern United States were asleep. In the rest of the world, people were going about their morning routines, commuting to work, preparing meals, having conversations about ordinary things. None of them felt anything unusual. None of them had any physical awareness that a wave was passing through them, through their bodies, through the atoms of their cells, through the molecules of the air around them, through the ground beneath their feet. But the wave was there. It was passing through all of it, including them. Let us reconstruct what was actually happening physically. The gravitational wave event, GW 150914, originated approximately 1.3 billion light-years from Earth. 1.3 billion light-years. The universe is approximately 13.8 billion years old, and this event happened 1.3 billion years of light travel time away. The light that was emitted by whatever electromagnetic radiation accompanied the merger if there was any, is still traveling toward us and will not arrive for another 1.3 billion years, by which time Earth will most likely no longer exist in any recognizable form. But gravitational waves travel at the speed of light, and the wave that LIGO detected had been traveling for 1.3 billion years from the moment those two black holes merged until the moment it reached Earth. When it arrived, it was carrying a strain of about 10 to the minus 21. This means that in a space 1 meter across, the gravitational wave was stretching one dimension of that space by about 10 to the minus 21 meters, while compressing the perpendicular dimension by the same amount, alternating back and forth as the wave passed through. Applied to a human body, roughly 1.7 meters tall, the maximum physical distortion the wave produced in any dimension was about 1.5 times 10 to the minus 21 meters. This is a number so small that it has no meaningful physical analogy. The nucleus of a hydrogen atom is roughly 1 femtometer, 10 to the minus 15 meters in radius. The stretching of a human body by GW 150914 was smaller than the nucleus of a proton by a factor of about 1 million. It happened. It was a real physical event. The atoms of your body were infinitesimally displaced by the passage of a wave generated by the merger of two black holes 1.3 billion light-years away, and you felt nothing. This is perhaps the most mind-bending aspect of the entire cosmic acoustics story. Not the scale of the energy involved, not the antiquity of the Perseus note, not the incomprehensible depth of the frequency range, but the fact that these events are not happening out there, at a safe cosmological distance, in a universe that operates separately from the one you inhabit. They are happening here. They are passing through your body. The wave that passed through every sleeping person on the eastern seaboard on September 14th, 2015, was a direct physical interaction between those people and the gravitational wave produced by the merger of two black holes 1.3 billion years in the past. A physical interaction, causal, real, just too small, by many orders of magnitude, to produce any perceptible effect in any biological sensing apparatus. And the GW 150914 event is not the only time this has happened. Since that detection, more than 90 gravitational wave events have been detected, which means more than 90 times in the last several years, at irregular intervals, the Earth has been crossed by a gravitational wave produced by the merger of black holes or neutron stars somewhere in the observable universe. These events are not becoming more frequent. They have been happening throughout the history of the universe at roughly the same average rate. We just did not have a detector capable of finding them before 2015. The waves were always passing through us. We simply had no way to know. There is a further implication here that goes beyond gravitational wave events from individual mergers. The universe, as we are about to discuss, has a background gravitational wave signal, a stochastic hum, produced by the superposition of gravitational waves from countless supermassive black hole mergers spread across the universe and across cosmic time. This background is always present. It is always crossing the Earth. It is crossing the Earth right now, as you read or listen to this. The strain amplitude is different from a single close event spread across a much wider frequency range and representing the incoherent sum of many sources rather than the coherent chirp of a nearby merger. But it is there, a gravitational background hum from the universe's entire merger history, propagating through spacetime, passing through every physical object on Earth, with every passing moment. The universe's acoustic activity is not intermittent, it is constant. We are inside it, always. Part 13. The first sound ever made. If the universe is acoustically active now, if it has been producing waves through plasma and spacetime throughout its history, then the natural next question is, when did it start? When was the first sound? When did the universe first produce a propagating wave disturbance in a real physical medium? And the answer to that question is much earlier than you might expect, earlier than the first stars, earlier than the first atoms, earlier, in fact, than any structure that we would recognize as ordinary matter. In the first 380,000 years after the Big Bang, the universe was too hot for neutral atoms to exist. Every time an electron was captured by a proton to form a hydrogen atom, a photon with enough energy would immediately ionize it again, splitting it back into a proton and electron. The universe was a hot, dense, opaque plasma, a uniform, ionized soup of protons, electrons, helium nuclei, and photons, all coupled tightly together by electromagnetic interactions. This early universe was, as we have established, a medium that can carry acoustic waves, and it had acoustic waves in it, not small ones. Waves driven by the density fluctuations left over from the inflationary epoch, quantum fluctuations in the density of the universe that were stretched to macroscopic scales by the exponential expansion of inflation, and then became seeds for structure formation. These fluctuations set up standing waves in the photon baryon plasma of the early universe, with the photon pressure providing the restoring force and the gravity of overdense regions providing the compression. The early universe was, in other words, ringing. These acoustic oscillations left a physical imprint on the structure of the universe that we can measure today. When the universe cooled enough for neutral atoms to form at around 380,000 years after the Big Bang, in the epoch called recombination the photons were released, streaming freely through the now neutral gas. These photons are what we now detect as the cosmic microwave background, the faint glow of the early universe visible in every direction on the sky, at microwave frequencies. And the acoustic oscillations that were happening in the photon baryon plasma before recombination left their imprint on the temperature fluctuations of the CMB. Different regions of the sky are slightly warmer or cooler than average by parts in 100,000, and the pattern of these fluctuations encodes the acoustic history of the universe from its first moments to the epoch of recombination. Cosmologists call these features acoustic peaks, peaks in the power spectrum of CMB temperature fluctuations that correspond to the harmonics of the acoustic oscillations in the early universe. Regions that were at maximum compression at the moment of recombination appear as temperature peaks. Regions at maximum rarefaction appear as temperature troughs. And the series of peaks and troughs in the CMB power spectrum represents the fundamental note and harmonics of the early universe's acoustic activity, the standing waves that were set up in the first few 100,000 years of the universe's existence. These are real acoustic features, driven by real physics, preserved in the structure of the oldest light we can observe. Astrophysicist Mark Whittle, a professor at the University of Virginia, has produced a reconstruction of what the early universe's acoustic oscillations would have sounded like if they had been in an air medium at frequencies humans can hear. His sonification takes the actual physical properties of the early universe's acoustic modes and translates them into audio using the real mathematical relationships between the modes. What you hear is a descending tone, a deep roar that drops in pitch over time, reflecting the cooling and expansion of the universe and the corresponding shift in the acoustic modes as the medium's properties change. It is not a sound chosen for effect. It is the actual physical structure of the early universe's acoustic field translated into a perceptible form. And it is remarkable to contemplate. The first sound the universe ever made, preserved in the oldest light that exists, reconstructed from cosmological measurements and rendered as a tone you can actually hear. The universe began with sound, not silence, and then a gradual awakening. Sound, from the very beginning, in a hot plasma that had the acoustic properties of a medium and was set vibrating by the quantum fluctuations of its own origin. Part 14. The background hum of reality. If the universe began with acoustic oscillations and has been producing waves through plasma and spacetime ever since, then there is a natural extension of this idea that brings us to one of the most recent and significant discoveries in astrophysics. Not a single event, not a single source, but a background signal, a persistent, low-frequency hum of gravitational waves permeating all of space at all times, produced by the superposition of countless individual sources spread across the observable universe. A cosmic audio background that is, in a real physical sense, always present, always here, always passing through everything. In June of 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, along with 4 other independent pulsar timing array collaborations around the world, announced strong evidence for the detection of a stochastic gravitational wave background. The signal was detected by precisely monitoring the timing of dozens of millisecond pulsars over 15 years and looking for correlations in their timing residuals, tiny deviations from the expected arrival times of pulsar pulses, that are consistent with the passage of gravitational waves through the space between us and the pulsars. The pattern they found, called the Hellings-Downs correlation after its theoretical prediction in 1983, is the specific spatial correlation function that a gravitational wave background would produce in a pulsar timing array. It is the fingerprint of a gravitational wave background, and NanoGrav found it convincingly in 15 years of data. The frequencies at which pulsar timing arrays are sensitive are in the nanohertz range billionths of a hertz, corresponding to wave periods of years to decades. These are far too low to be produced by the stellar mass black hole mergers that LIGO detects. The likely sources of the gravitational wave background in the nanohertz band are supermassive black hole binaries, pairs of black holes with masses of millions to billions of solar masses at the centers of galaxies that have merged. When 2 galaxies merge, their central black holes eventually find each other through dynamical friction, form a binary, and spiral together over billions of years, emitting gravitational waves throughout the process. There are estimated to be tens of millions of such binaries in the observable universe at any given time, each contributing its own gravitational wave emission to the background. The incoherent sum of all of these signals is the hum that NanoGrav has detected a gravitational wave background that has been building for as long as galaxies have been merging, which is most of the history of the universe. This background is not a signal from out there, far away, in the universe at large. It is local. It is here. It is passing through Earth right now, stretching and compressing spacetime at nanohertz frequencies, with a strain that is many orders of magnitude too small to feel or detect with any instrument short of a galaxy-scale gravitational wave detector. But it is real. It is physical. And it has been here, undetected and unnoticed, for the entire history of civilization. Every generation of humans that has ever lived was immersed in this gravitational wave background without knowing it. Every historical event, every war, every artistic creation, every scientific discovery, all of it happened inside a gravitational wave background produced by the merger history of galaxies across the observable universe. The hum of the universe was always present. We only learned to recognize it in the last few years. Looking forward, the European Space Agency's LISA mission, the Laser Interferometer Space Antenna, planned for launch in the mid-2030s, will extend gravitational wave detection to frequencies between the millihertz and nanohertz bands, a range currently inaccessible because Earth's seismic noise drowns out any ground-based detector at these frequencies. LISA will consist of 3 spacecraft in a triangular formation separated by 2.5 million kilometers, connected by laser beams that will measure relative distance changes at levels comparable to LIGO's sensitivity. It will be capable of detecting the gravitational waves from supermassive black hole mergers when they happen, not the background hum, but individual events with signal-to-noise ratios high enough to reconstruct the source properties in detail. LISA will also be capable of detecting the gravitational wave signal from the early universe itself, the cosmological background left over from inflation, and from the phase transitions of the early universe, potentially including signatures of physics beyond the standard model. We are, in other words, just beginning to develop the ears to hear the universe's full acoustic range. Part 15. Signals we do not understand. Here's something I want to be honest with you about, because I think it actually makes this whole story more interesting, not less. Everything we've covered so far, the sun ringing, the Perseus note, the gravitational wave background humming through your body right now, all of that fits. It's strange, it's mind-bending, but it fits inside a framework we understand. Plasma acoustics, magnetohydrodynamics, general relativity, unusual physics, but physics we've had time to get comfortable with. The math checks out. The predictions match the observations. The universe, in those cases, is doing exactly what the equations say it should. But the universe isn't always that cooperative, because sitting out there, in the data from radio telescopes around the world, are signals that don't fit cleanly, phenomena that the framework hasn't fully swallowed yet. And in a story about the cosmic soundscape, about what the universe is actually doing at frequencies and energies, we were never built to detect those anomalies, deserve at least as much attention as the things we understand. Maybe more, because if the history of astrophysics teaches us anything, it's that the things we can't explain are usually pointing towards something real. Fast radio bursts, FRBs, are exactly what the name says. Brief, violent, intense bursts of radio waves arriving from cosmological distances. And when I say brief, I mean it. Some of them last microseconds. The longest last a few milliseconds. That's it. A blink is slow compared to what we're talking about. In that tiny window of time, a single fast radio burst can release as much energy as the sun emits over 3 entire days. Think about what that means for a moment. 3 days of the sun's output compressed into a millisecond, released somewhere out there, billions of light years away, in a burst so brief that if you were watching the source with the right detector and you blinked, you'd miss the entire event. We first detected them in 2007, and, for a while, no one could agree on whether they were one-time events, some kind of catastrophic, unrepeatable explosion, or whether the same sources could fire more than once. That question mattered a lot, because the answer would dramatically narrow down what could possibly be producing them. Now we know. Some repeat. The same source, sometimes bursting multiple times, with no obvious regularity or trigger. No pattern that suggests a simple orbital cycle or a predictable physical process, just bursts. Plural, from the same location in the sky, arriving at intervals that our current models don't cleanly predict. Others appear to be one-time events. Different mechanism, maybe, or the same mechanism but with different outcomes. We don't fully know. The leading explanation, and I want to stress the word leading, not proven, involves magnetars. Magnetars are neutron stars, with magnetic fields so powerful they make regular pulsar fields look like fridge magnets by comparison. We're talking about fields of roughly 10 to the 15th Gauss. For context, Earth's magnetic field is about half a Gauss. The surface of a magnetar is an environment so extreme that our understanding of physics, specifically dense matter physics, strong field electrodynamics, and plasma behavior at energy scales we've never replicated in any laboratory, is genuinely being pushed to its limits. The idea is that something like a starquake happens on the magnetar's surface or in its crust. The magnetic field, under enormous tension, suddenly snaps and reconfigures, releasing an enormous burst of electromagnetic energy in the process. That's the fast radio burst. A crack in the crust of a dead star, amplified by a magnetic field of incomprehensible strength, producing a flash of radio waves powerful enough to be detected across billions of light years. It's a compelling picture, and for some FRBs, it probably is what's happening. But here's the thing, and this is the honest part. Magnetar models don't fully explain all the properties we're seeing. Some fast radio bursts show internal structure, substructure within the burst itself, variations in intensity, frequency drifts, patterns that look like they might be telling us something about the physical geometry of the emission region or about some kind of modulation happening at the source. Others arrive in groups, multiple bursts, separated by spacings that have been claimed to show periodicity, a regular rhythm. Not all of these claims have held up under scrutiny, but the patterns keep appearing in the data, and the framework keeps not quite being able to account for all of them. That's not a failure of science. That's science working exactly as it should, data arriving before understanding. Anomalies accumulating until a framework either expands to contain them or breaks and gets replaced. Right now we are in the accumulation phase for fast radio bursts, and the honest position is that we are dealing with physical environments at the extreme edge of what current theory can describe, and we should expect surprises. It would be genuinely strange if Magnetar's objects at the boundary of known physics behaved in ways that fit tidily inside models built from less extreme conditions. And then there are the glitches. Pulsars, as we've established, are rotating neutron stars, cosmic metronomes of extraordinary precision, ticking with a regularity that puts atomic clocks to shame. The stability of their rotation rate is part of what makes them so useful. It's why we can use them to detect gravitational waves, why a deviation in their timing is meaningful signal rather than noise. But sometimes a pulsar glitches. Suddenly, on timescales too short to resolve with current instrumentation, its rotation rate increases. Not decreases, increases. The pulsar spins up, and then, over weeks or months or sometimes years, it gradually relaxes back toward its previous rotation rate. Not all the way, usually. The pulsar ends up spinning slightly faster than it was before the glitch, and then the long, slow recovery begins. This shouldn't happen in a simple model of a rotating neutron star. Pulsars are supposed to be spinning down over time, losing energy to magnetic dipole radiation and particle emission. So what's making them suddenly spin up? The leading explanation involves the internal structure of the neutron star. Specifically, the idea that a neutron star has a solid crust on the outside and a superfluid interior. Superfluids are bizarre states of matter that flow without friction and exhibit quantum mechanical behavior at macroscopic scales. The theory is that the superfluid interior can be rotating slightly faster than the crust, storing angular momentum like a spinning flywheel that's only loosely coupled to the outer shell. When something triggers a sudden coupling, some kind of crust quake, some reconfiguration of the internal structure, angular momentum transfers from the superfluid to the crust, spinning it up abruptly. It's a plausible mechanism. It fits the general shape of the observations, but the details don't always match. Some glitch magnitudes and recovery timescales fit the model, and some don't. Some pulsars glitch frequently, others rarely, and the pattern of who glitches and when doesn't have a clean explanation. The superfluid interior of a neutron star is, frankly, one of the most exotic states of matter in the known universe. Matter compressed to nuclear density, cooled enough for quantum condensation effects to operate at stellar scales. And we are not going to describe its behavior perfectly with models built from observations of matter in much less extreme conditions. The pulsars, in other words, are still surprising us. These are some of the most studied objects in radio astronomy, objects we've been monitoring for decades, objects whose timing data fills enormous archives, and they still produce behavior that our best models don't fully account for. Here's the thread connecting all of this to the larger story. The stochastic gravitational wave background, the hum of supermassive black hole mergers across the entire observable universe, was theoretically predicted for decades before we detected it. The cosmic microwave background, with its acoustic peaks imprinted by pressure waves in the early universe, existed long before we had a telescope sensitive enough to measure it. Gravitational waves from stellar mass black hole mergers were predicted by general relativity nearly a century before LIGO finally heard the first chirp. In each case, the pattern is the same. The universe was already doing the thing. The signal was already there. The waves were already propagating, the background was already humming, the imprint was already frozen into the oldest light. We simply hadn't built the instruments or developed the theoretical frameworks to hear it yet. The history of cosmic acoustics is specifically a history of the universe being more acoustically active than we thought. More sources, wider frequency ranges, more exotic media, more energetic events, and our detection capabilities slowly, painstakingly catching up. Fast radio bursts and pulsar glitches aren't anomalies in the sense of things that will break physics. They're almost certainly anomalies in the sense of things that are going to teach us something important about extreme matter, strong field electrodynamics, and the behavior of plasma and quantum matter at densities that have no analog in any laboratory we've ever built. They're pointing toward parts of the cosmic soundscape we haven't mapped yet, regions of the frequency and energy landscape where our instruments are just beginning to reach, and our theoretical frameworks are just beginning to strain. The universe's acoustic reality almost certainly extends further and gets stranger than what we've detected so far. Every time we've improved our instruments, it has. Every time we've opened a new observational window, X-ray astronomy, gravitational wave detection, pulsar timing arrays, the universe has been louder than the previous window suggested. There is no reason to think we've reached the end of that pattern. The signals we don't understand aren't gaps in the story. They're the beginning of the next chapter, already broadcasting, waiting for us to build something sensitive enough to hear what they're actually saying. Part 16, the final realization. We have come a long way in this video. We started on the moon boots in grey dust, total silence, the most disorienting sensation the Apollo astronauts described from the entire mission. Not the weightlessness, not the alien terrain, the silence. And from that silence, we built a case. We took apart the textbook definition of sound, examined what plasma actually is and why it dominates the universe's visible matter, looked at what the sun is doing right now at frequencies 10,000 times too low for your ears, followed the electromagnetic songs of the planets, listened to the precision ticking of dead stars spinning hundreds of times per second, and then pushed all the way out to the most extreme acoustic events. The universe produces a black hole holding a single note for 2.5 billion years and a gravitational wave event that was briefly louder than every star in the observable universe combined. That is a lot of ground. And individually, each of those things is remarkable, worth a video on its own, worth spending time with. But I want to stay here for a moment at the end, because the individual examples are not actually the point. The point is what you get when you hold all of them at once, when you stop looking at the pieces and let the full picture assemble. Because what that picture shows is something qualitatively different from any single fact about a ringing sun or a deep black hole note. It shows you the actual operating condition of the cosmos, not the exotic edge cases, not the dramatic anomalies, the normal, continuous, everywhere at once acoustic reality of the universe you live in. Right now, not in some distant galaxy, not in some exotic astrophysical environment, but right now, in this exact moment, the Sun is resonating in millions of simultaneous acoustic modes. The pressure waves inside it, driven by convective turbulence near its surface, are bouncing off its interior structure, interfering with each other, building up into standing waves that probe different depths, that encode information about the temperature and density and rotation of the solar interior. This has been happening for 4.5 billion years. It will continue for another 5 billion. It is not an event. It is a condition. Jupiter's magnetosphere, right now, is broadcasting electromagnetic plasma waves into the solar wind. The largest coherent structure in the solar system, larger even than the Sun itself in physical extent, is churning with wave activity driven by the most intense planetary magnetic field in the solar neighborhood. Saturn's rings are generating electrostatic discharges. The magnetosphere of Earth, a few thousand kilometers above where you're sitting, is producing chorus waves rising, chirping electromagnetic oscillations that sound, when translated, unnervingly, like a forest at dawn. These things are not waiting for a measurement to become real. They are real. They are happening. They simply require instruments we didn't have until recently to detect. The Crab Pulsar is ticking at 30 times per second. Right now, it has been doing exactly this since a star exploded in 1054 AD, and astronomers in China and the Arab world looked up at the sky and saw a new star bright enough to read by at night. That explosion was witnessed. It was written down. It happened in human recorded history, and the remnant has been ticking with atomic clock precision every single second since. 30 pulses per second for nearly 1,000 years. You were not listening, but it was broadcasting. The Perseus black hole is still driving pressure waves through the hot plasma of the galaxy cluster, 240 million light-years away. The wave that the Chandra X-ray Observatory detected, the B-flat, 57 octaves below middle C, is still propagating. The cycle that started 2.5 billion years ago, before complex life had appeared on Earth, has not stopped. The black hole does not know we detected it. The wave does not care whether there is a telescope sensitive enough to see the ripples it makes in the X-ray emission of the intracluster gas. It propagates because the physics demands it. That is the only reason anything in the universe does anything. And gravitational wave events, black holes and neutron stars, merging somewhere in the observable universe, are occurring at a rate of multiple events per week, based on current detection rates. Multiple times per week, somewhere out there, two massive objects that have been spiraling toward each other for billions of years finally close the last distance between them, merge in a fraction of a second, and release a burst of gravitational wave energy that briefly rivals the electromagnetic output of the entire observable universe. The wave expands outward at the speed of light. Eventually, attenuated by the enormous distance it has traveled, it crosses Earth. It passes through everything, including you, and you feel nothing because the strain it induces in any physical object is smaller than the nucleus of a proton by a factor of millions. None of this is waiting for you to observe it. None of it requires your awareness. None of it is performed for a listener. The universe's acoustic activity is not a feature designed to be interesting. It is the unavoidable consequence of the physical laws that govern matter and energy laws that make plasma compressible, laws that make magnetic fields wave-like, laws that make spacetime an active, dynamic medium that responds to the presence and motion of mass. These laws don't have an off switch. They don't take a break when nothing is watching. They are what the universe is. And acoustic wave propagation through every available medium is one of the most direct consequences of being that kind of universe. This is the thing I want you to sit with, because I think it genuinely changes something about the mental picture most of us carry around. We were taught that space is silent. And in the specific, narrow, technically defensible sense of human ears cannot detect pressure waves in interplanetary vacuum, that is true. But the mental picture that fact creates a cosmos operating in quiet, a universe where the enormous distances between objects feel somehow peaceful, where all the drama of stars and black holes and colliding galaxies plays out against a backdrop of pristine silence, that picture is not just incomplete. It is, in the most important sense, the opposite of the truth. Silence is the exception. It is local. It is what you get in the specific thin patch of interplanetary vacuum around one particular rocky planet where listening creatures happen to evolve. The universe at large is not quiet. It operates across frequency ranges that span 30 or more orders of magnitude, in media ranging from stellar plasma to the fabric of spacetime itself, at energy scales that make the entire acoustic output of Earth, every thunderstorm, every ocean wave, every earthquake, every human voice that has ever spoken look like a single instrument playing a single note at the far edge of an infinite concert hall. There is a philosophical point underneath this that I think is worth being explicit about, because it's easy to hear all of this and still not quite let it land. Human beings evolved in a very specific acoustic environment. We developed ears because detecting pressure waves in a nitrogen-oxygen atmosphere at frequencies relevant to predators, prey, and other humans was useful for survival. That is the entirety of the reason our hearing range is what it is. Not because those frequencies are the most important ones in the universe. Not because that range reflects the fundamental acoustic character of the cosmos. Simply because it was useful for one species on one planet for a few 100,000 years. Evolution optimized us for survival in a specific environment. It was never trying to give us accurate perception of the universe as it actually is. Those are not the same goal, and evolution has no interest in the second one. The gap between what we can hear and what the universe is producing is not a small gap. It is not the gap between seeing most of a painting and missing a few brush strokes at the edges. It is the gap between standing in a soundproof room and standing in the middle of a full orchestra at full volume. We have been in the soundproof room for our entire existence as a species. We could look through the glass. We could see the musicians moving. We could watch the strings vibrate, see the conductor's arms, observe the percussion impacts, and we concluded, reasonably, from the absence of anything we could hear, that it was probably not very loud in there. It was not a stupid conclusion. It was the only conclusion available given our instruments. But it was wrong, dramatically, fundamentally wrong. The room was full of sound. We just couldn't hear it. The Perseus note is still playing. A B flat, 57 octaves below middle C, propagating through plasma at tens of millions of degrees. It started 2.5 billion years ago, when the most complex life on Earth was a single cell with a nucleus, no tissue, no organs, nothing that would be recognizable to any biologist as multicellular. The wave has been traveling through that cluster ever since. It was propagating when the first multicellular organisms appeared. It was propagating through the Cambrian explosion when complex animal body plans suddenly diversified in the fossil record 500 million years ago. It was propagating when the dinosaurs appeared, when they dominated, when the asteroid hit and the age of mammals began. It was propagating when the first hominids walked upright in East Africa. It was propagating through the entire span of human civilization. Every empire, every language, every religion, every scientific revolution, every war, every artistic achievement, every moment of human history, the whole of recorded human time, compressed into the last tiny fraction of the wave's journey. It is playing right now, this exact moment, 240 million light-years away. It will still be playing when the Sun exhausts its hydrogen fuel and expands into a red giant, swallowing the inner planets. It will still be playing when the Milky Way and Andromeda complete their merger billions of years from now, when the night sky is full of new star formation triggered by colliding gas clouds. It will still be playing when the last stars in the universe exhaust their fuel and cool into darkness. The black hole does not stop because there is no one left to hear it. The wave propagates because the physics demands it. The universe does not require a listener. It never did. And here is the part that I find most genuinely strange to sit with stranger, in some ways, than the scale or the energy or the frequency. The gravitational waves that pass through Earth multiple times per week are not passing through the Earth in some abstract or metaphorical sense. They are passing through your body, through the atoms of your cells, through the molecules of whatever you're sitting on, through the air around you. The geometry of spacetime in your immediate vicinity is being stretched and compressed right now by waves generated by massive objects merging somewhere in the observable universe. The strain is so small, smaller than a proton, by many orders of magnitude that no biological or technological instrument casually deployed in everyday life could detect it. You have no sensory access to it whatsoever, but it happened. It happens. Multiple times per week, you are physically inside a gravitational wave event. Your atoms are displaced. The space you occupy is briefly different. A direct physical interaction, causal and real, between your body and the merger of black holes or neutron stars light years away. And you have never once felt it in your entire life because you were not built with the right kind of detector. That is not a metaphor. That is a literal, physical description of your relationship to the universe's acoustic activity. You are immersed in it. You are inside it. You are not observing it from some safe vantage point outside. The waves are here, with you, passing through you continuously. The gravitational background hum the incoherent superposition of gravitational waves from every supermassive black hole binary merger in the universe's history, building up over billions of years into a stochastic background, is here right now, in the room you're in, at nanohertz frequencies, stretching and compressing spacetime at amplitudes far too small to feel. It was there during every conversation you've ever had, every night you've ever slept, every significant moment of your life. The universe's merger history was humming through the room, unnoticed and undetectable, as real as the floor under your feet. What we have built, the telescopes, the radio arrays, the X-ray observatories, the laser interferometers, the pulsar timing networks, these are our first, primitive attempts at building ears for the universe's actual frequency range. They are extraordinarily limited compared to the full acoustic spectrum of the cosmos. They operate in narrow windows. They require engineering effort of staggering precision to extend sensitivity by even one more order of magnitude. They are vulnerable to seismic noise and thermal noise and quantum noise, and the near impossibility of isolating any instrument from the acoustic environment of an active planet. They are, cosmically speaking, rudimentary, and with these rudimentary instruments, we have already heard more than any generation before us ever imagined. We have heard the sun ring. We have heard the planet's plasma songs. We have heard the chirp of two black holes becoming one, a sound that swept upward through the audio range in less than a second and carried energy equivalent to 3 solar masses converted entirely into gravitational waves. We have detected the background hum of galaxy mergers across the entire observable universe. 15 years of pulsar timing data slowly resolving into the Hellings-Downs correlation that tells us the hum is real. We have found the acoustic imprint of the Big Bang itself, frozen into the temperature fluctuations of the oldest light, the standing waves of the early universe, encoded in the cosmic microwave background, for anyone with a sensitive enough detector to read. We have found the lowest note ever measured, held by a black hole for longer than complex life has existed on Earth, and we are just getting started. LISA, the Laser Interferometer Space Antenna, 3 spacecraft in a triangular formation separated by 2.5 million kilometers, is designed to open the millihertz frequency window, the band between what LIGO hears and what pulsar timing arrays hear, currently inaccessible from the ground because Earth's seismic noise drowns everything out. In that band sits the gravitational wave signal from the early universe to ripples left over from inflation and from the phase transitions of the first moments, potentially including signatures of physics we haven't discovered yet. The next generation of instruments will hear things we cannot currently predict, because every time we've opened a new observational window, the universe has been doing something we didn't expect. So I want to leave you with this. You are not a visitor to a silent cosmos, passing through emptiness on a rock, observing the universe from a safe remove. You are inside the symphony. You have always been inside it. Every atom of your body, right now, is being crossed by gravitational waves and plasma oscillations and electromagnetic emissions from every star and plasma environment in the observable universe, attenuated by distance but physically present. The universe's acoustic output is not happening somewhere out there. It is happening here, in the space you occupy, at frequencies and in media that your biology was never configured to register. The silence you experience when you look up at the night sky is real. It is the silence of an organism whose sensory range spans about 10 octaves in a universe whose acoustic range spans 30 or more orders of magnitude. It is the silence of a detection apparatus not built for the task, not a failure of the universe to produce anything, but a failure of our particular biology to receive most of what is being produced. The universe was not waiting for us. It was not quiet before we arrived, and it will not fall silent when we are gone. The Perseus note started before our ancestors were cells, and will continue after the last star dies. The gravitational background was humming through empty space long before Earth formed. The Big Bang itself began with sound acoustic oscillations in a hot plasma that imprinted their pattern on the oldest light in existence. The only silence was ours. It was always only ours. And for the first time in the history of this species, we are slowly, imperfectly, with instruments that are primitive by any cosmic standard, beginning to hear what we were always inside. That should feel like something. I think it does.